Okay, hi guys.
Hi.
Okay, for the past 2 weeks, I've been studying about two chapter that I think is closely related to our engineering process, which is first the Stokes theorem, and the second one is called the triple integral in spherical formula. Okay, so first of all is the Stokes theorem. So, in general, Stokes theorem, which is also known as Kelvin-Stokes theorem, after Lord Kelvin and George Stokes, is the fundamental theorem for curves, or simply the Kerr theorem. So, Aiman, can you please help me to explain about the question related to Stokes theorem that I asked you several days ago?
Of course. Okay, so this is a simple question that can help you to understand the Stokes theorem. The question is from the figure 3, by relate to the Stokes theorem, prove that the direction of magnetic field on the flat surface of the hemisphere is equal to the direction of magnetic field on the curved surface of the hemisphere along the z-axis. Given the spherical formula is x square plus y square plus z square equal to 1 and z equal to 0, and the vector field fxyz equal to the yi minus xj plus zk. So from this formula, we know that the Stokes theorem is an equality between two relative different things. On the left hand side is the circulation around the curve, and the right hand side we know that the normal direction, the curl of f dotted with the n. I have a parameterization for that boundary curve it into the theta boundary curve into the unit circle, so I'm going to write this as a cos theta I plus sin theta j plus 0k. Why 0k? 0 in the k hat because that boundary circle is in the xy plane. It has no hat component. So now I'm actually going to compute that the line integral along the curve. So what we need to integrate is the field f dotted with the dr or r prime. So the field component is f equal to the yi minus xj plus zk dotted with the r prime, which is negative sine theta I plus 0 theta j plus 0k. So we integrate and we get the answer negative 2 pi. So next we do for the surface integral of the curve f dotted with the n ds. So first we need to find the curl of f, which is, and we get the negative 2k, and dotted with the n ds. The n value is a k hat because the normal vector is just k hat, so the n value is the k hat. And so we get the answer negative 2 pi. So we can see that we get the exact same answer. So proof that we can see that the same answer into the right hand side and left hand side.
Thank you, Aiman. I think that's a very good explanation. Okay, thank you, Aiman, for that explanation. I think I can quite catch how to simply answer that type of question. So, secondly, the triple integral in spherical coordinate. So, in general, in calculus, an integral is the mathematical object that can be interpreted as an area or a generalization of an area. So, Dani, would you mind helping me to answer the question about triple integral?
Yeah, sure. So, I have to take a look the question that you have given to me. So, the question is, use spherical coordinates to find the volume of the region outside the sphere P equal to 2 cos pi, and inside the half sphere T equals to 2 with phi set 0 pi over 2. And first of all, we need to start the calculation with the sketches. done the sketches, and this is the sketches. And next, I have do the calculations with p equals to 2 cos phi, and same with the x square plus y square plus z square and equals to 2z. And x square plus y square plus z minus 1 square equals to 1. And this is the equation for the sphere. And p is equals to 2, is a sphere radius 2, and phi set pi 0 pi over 2 says we only consider the upper half of the sphere. And we will start the triple integration calculation, and this is the calculation. Please pardon my writings. And after all, we have after we done the calculation, we need to introduce the substitution, which is u equals to cos phi negative sine phi d phi. And after we have done the substitution, we have simplified, and after all, we get the answer, which is the v is equal to 4 pi. You get it?
Oh, yeah. I think I get it. I think I can quite get the hang of it. Danny, can you please show me like the real life example of the kind of question that you get?
Yeah. For me, in the engineering life, we can apply this kind of calculation method, which is triple integration in spherical coordination, to find out the certain parts of the metal volume for the casting. What is casting? Process of the creating metal objects by pouring liquid metal into molds. So, to find the molds volume, we need to find out the certain part of that mold, which is we have a different volumes. So we can use this method, which is triple integration in spherical coordination method.
Hey man, how about you? Can you please relate the question that you explained earlier with real life engineering example?
Yes, of course. Okay, in the context of the Stokes theorem, we can relate it with the magnetic field. We know that the magnetic field is a vector field that describes the magnetic influence of moving electric charge, electric current, and magnetic material. Magnetic fields are produced by moving electric charge and the intrinsic magnetic moment of elementary particle. So, we can use the second right-hand rules, sometimes called the right-hand grip rules, to determine the direction of magnetic field created by a current. So, is a sample the related engineering problem that we can relate to the Stokes theorem.
I see. So I guess the title really relates to our engineering students. So I guess that's it for our discussion today, and I think this is a really good example of a good presentation and discussion. So thank you guys for your help, and I'll see you guys later. Bye.